Stream processing has been around since the 1990s, but what is it actually used for? Let's go through the major categories, because each one has a fundamentally different character. The oldest use case is complex event processing, or CEP. Developed in the 1990s, CEP is essentially pattern matching on event streams. Think fraud detection. If a card is used in New York, then in London 5 minutes later, flag it. CEP allows you to specify rules to search for certain patterns of events in a stream. The system stores queries long-term and continuously runs events past them. This is the reverse of a normal database, where data is stored in queries are transient. CEP implementations include Esper, IBM InfoSphere Streams, Apama, TIBCO Streambase, and SQL Stream. Apache Samza is gaining SQL support for this style of querying. Stream analytics is the second major use. Where CEP looks for specific event sequences, analytics aggregates over large numbers of events, measuring the rate of some event type, calculating rolling averages, detecting unusual metric values compared to the same time last week. These are computed over fixed time windows. Analytics frameworks include Apache Storm, Spark Streaming, Flink, Concord, Samza, and Kafka Streams. Hosted services include Google Cloud Dataflow and Azure Stream Analytics. Third, maintaining materialized views. When a CDC stream flows through a stream processor and updates a derived data store, that's a materialized view being maintained. Samza and Kafka streams are particularly good at this because they build on Kafka's log compaction. They can maintain views that stretch back to the beginning of time, not just a limited window. Fourth, search on streams. The Elasticsearch Percolator feature does this. You store queries and run documents past them, alerting you when a news article matches your search criteria. The documents run past the queries, exactly like CEP. Next up, the hardest part of stream processing: reasoning correctly about time. Here's a scenario that will break your intuitions. You're building a stream analytics system measuring requests per second. Your stream processor goes offline for maintenance. It comes back up, processes the backlog of events from the last few minutes, and suddenly your dashboard shows a spike to 50 requests per second when the actual rate was a steady 10 all along. What happened? You confused event time with processing time. These are two completely different concepts, and mixing them up causes bad data. Event time is when the event actually happened, the timestamp embedded in the event itself by the producer. Processing time is when the stream processor sees the event. The gap between them can be enormous. A mobile device goes offline for 3 hours, reconnects, and floods the processor with events that all have timestamps from 3 hours ago. A network partition delays events by minutes. A stream processor restart causes a backlog replay. There's a beautiful analogy from the Flink community. Think about Star Wars movies. Episode 4 was released in 1977, Episode 5 in 1980, then Episodes 1, 2, 3 in 1999 to 2005, prequels released after the sequels. If you watch them in release order, the processing order is 4, V, 1, 2, 3, completely different from the narrative order 1, 2, 3, 4, V. The release date is the processing time. The episode number is the event time. As humans, we can cope with this. Stream processing algorithms must be specifically designed to handle it. If you use processing time for windowing, a stream processor restart introduces a phantom spike. The backlog is processed with current timestamps, making it look like a traffic surge. If you use event time, you need to handle straggler events that arrive after the window they belong to has already closed. Google Dataflow handles late data with watermarks, a heuristic estimate of how far behind the slowest event might be. Straggler events can either be dropped or used to publish a correction to the previously published window result. The framework tracks which events it's still waiting for. This is the right engineering trade-off, and understanding it is what separates serious stream engineers from everyone else. Once you commit to event time processing, you need to divide the infinite stream into finite chunks to compute aggregations. These chunks are called windows. There are 4 fundamentally different window types, and choosing the wrong one for your use case produces wrong answers. Tumbling windows are fixed, non-overlapping time periods. Think of them as buckets. A 1-minute tumbling window collects all events from 12 hours to 12 hours and 59 seconds, closes, emits a result, then starts a new bucket from 12 hours and 1 minute. Events belong to exactly one bucket. These are the simplest and most intuitive. Use case: hourly batch totals, daily sales summaries. Hopping windows are also fixed size periods, but they overlap. They hop forward by a step smaller than their size. A 5-minute window that hops every 1 minute generates a new result every minute, but each result covers the last 5 minutes. Events can belong to multiple windows. Use case: smooth rolling metrics, moving averages. Sliding windows are triggered by events rather than clock ticks. A sliding window of the last 5 minutes means, at any point in time, look at all events from the past 5 minutes. Every event arrival opens a new window. These are continuous and natural for user session analysis. Use case, show me all events that happened within 5 minutes of this event. Session windows are the most sophisticated, they're activity-based rather than time-based. A session window groups all events that occur within a maximum gap of inactivity. If a user is active for 30 minutes, leaves for 2 hours, then comes back for 10 minutes, you get 2 sessions. The window closes after a configurable inactivity timeout. Use case, user session analytics, clickstream analysis. All 4 window types must handle the straggler problem. What do you do when an event arrives after its window has closed? Your framework needs a policy: ignore it, update the result, or emit a correction. Flink, Spark Streaming, and Google Dataflow all implement these 4 window types with late data handling. Joining streams together is one of the most powerful and most misunderstood features in stream processing. There are 3 completely different types of stream joins, and they require different approaches. The stream join is the most complex. Both sides are infinite streams. To join them, you must maintain state on both sides, a buffer of recent events, and match incoming events against buffered events from the other side. For example, joining add click events with add impression events to compute click-through rates. An impression event arrives, you buffer it, waiting for a matching click. A click event arrives, you check the buffer for a matching impression. The buffer size determines how far back in time you're willing to look for a match. Events in Flink and Spark Streaming use time windows to bound the buffer size. This join requires buffering state, which grows without bound unless you set a window. The stream table join is also called an enrichment join. One side is a stream, the other side is a database table, specifically, a local copy of the table that the stream processor maintains. As each event in the stream arrives, it's enriched with data from the table copy. For example, enriching each web request event with user profile information by joining on user ID. The table copy must be kept up to date, typically via a CDC stream from the source database. The key insight: the stream processor needs a local copy of the table. A remote database call per event would be too slow at stream throughput. The table join materializes a join of 2 tables that are both being updated. Both input sides are CDC streams of database changes. You maintain a local materialized view of both tables in the stream processor and update the join result as either table changes. Kleppmann uses Twitter's home timeline as an example. When you follow someone, you need their recent tweets added to your timeline. When they tweet, you need it added to all follower timelines. The join of users and tweets, maintained as a materialized view, is a table join. What makes all 3 joins challenging in stream processing is state management. How much state do you keep, how long, and where? This question connects directly to fault tolerance, which is where we're headed next.